For your warm-up questions, they were regarding the categories that we talked about yesterday. I did a preliminary introduction to the periodic table's couple layers of this organization. Major element types and then individual featured columns. We're not doing every column. We're just doing featured columns, right? And I introduced some of their physical and chemical behavior stuff. But before we transition over to another layer of the periodic table, which you started actually looking at in yesterday's puzzle activity, why we organize things in rows and columns. What else about the rows and columns does that periodic table tell us? Let's do a quick review. Somebody, please give me a little overview on the three types of elements. Just name them for me. What are the three major categories of elements? Min.
Metal, non-metal, metalloid.
Metal, non-metal, metalloids. And what's that special subcategory of metals? Transition metals. Okay. What's some facts about metals? What's some facts about metals? Liam? They want to lose an electron in general. And if you're what type of column of metals, you want to lose one? Alkali, because alkali ends with an I, which looks like a little one, right? Alkali, column 1. Okay, what else do we know about metals? Lachlan? They're great conductors of heat and electricity. It's why you cook in a metal frying pan and not an oxygen pan. Okay, what else do we know, Hallie? They're usually dense as solids, boom, 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 right? What if I just push my sink and it just over? That would be very disconcerting, right? Okay, what else do we know about non-metals? The second category, non-metals. Roman? Yeah, they're usually gas or liquid at room temperature. What else do we know, Drea? Tell me about a non-metal fact. Roman just said that. You're not wrong. You're just not right. Yeah, they're poor conductors of heat and electricity. Have you ever plugged your phone into a hydrogen wire? No. Okay. What about chemically? What about them chemically, Matthew? What about them chemically? E negative stands for what subparticle? What subparticles? A subparticle? Yeah. Things inside of an atom. We've got, think about your isotope quiz, right? You got protons, neutrons, and electrons. Yes. And electrons carry a what charge? Negative. So then what does E negative probably stand for? Electrons. Yes, sir. Okay, electrons. Excellent, excellent. They tend to gain or share electrons. They're kind of a negative hog. Okay, they just love it. They love it. It's like people that love the tea. Me, I love the tea. Tell me all the tea, the gossip, ooh, who did that? Who said that? Just kidding. I'm better than that. I don't read cosmopolitan magazines. I just learn about your lives, and that's exciting enough. Okay, what about metalloids? What's cool about metalloids? Metalloids, Juan? You were tardy, I know, yesterday, so you should have watched the video lecture for the part that you missed. And did you? Okay. Oh, you were busy? With what? Oh, get in the gains. Get in the gains. Not seeing much right now. I think it'd be more fruitful to get the mental gains, eh? So you need to watch that video during seminar or at the last 30 minutes of class when I give you time to work. Stay up to date. Okay, that's right. Danny. Tell me about a metalloid.
They have metal and non-metal properties.
Yeah, they tend to look like they're metals, but they tend to act like they're non-metals. What else? They chemically behave like a non-metal. Exactly, which means that they are going to what, Matthew? If they behave like a non-metal. If they chemically behave like a non-metal, they what then? What does a non-metal behave like? You literally just said it 2 seconds ago. You got this. That's right. I'm going for you today. Keep you on your toes.
What did I say 2 seconds ago?
Something you read off the paper about probably 2 inches up on your iPad. What about electrons? Chemically behave as a nonmetal. What do nonmetals do when they chemically react with something?
Gain or share with it?
There we go. There we go. Remember, guys, everything that you are learning in class, you need to actually digest because you're not going to have a note paper. I never, ever give you little flashcard, little help paper. No, unless you have an accommodation, okay, that is legally bound for me to offer that, which is right now, none of you actually have that as part of your accommodations. If you even have accommodations, you are not getting a note card. It all comes from here. So you need to work up here. Okay, so keep yourself on your toes. All right, excellent. So describe now alkali, alkaline, and halogen. Now we're zooming in on columns, on families. So alkali, Jose, tell me something about an alkali. Liam already gave us a sneak peek. It likes to take on a 1+ charge, which means it has what? To get that 1 positive charge, what must have happened to it? It's what? It loses an electron. What else do we know about the characteristic of alkali? Bryce, what's something that we know about them?
It does not include H.
Does not include H, hydrogen. That's a weird one. H kind of dibbles and dabbles in the trends, but then it kind of makes its own. Okay. What else do we know about them? If you scroll down a little further, when we zoomed in even more, what else do we know about alkali itself? They're highly reactive. They're the most reactive of all the metals. Okay, most reactive. All right. What do we know about alkaline? What are alkaline metals? Where do we find them on the periodic table? Diego? Second column, because it's a longer word than alkali, so you know you had to move into the next column, alkaline. Okay, second, alkaline, second column. Okay, what do we know about alkaline, Mika? Yes. They're the most reactive of the metals. Good clarification. What else do we know about alkaline, Alex? They are reactive, but Jocelyn? Not as reactive as alkali because they want to, Aislinn? They want to lose 2 valence electrons to take on a charge of Valeria? To take on the charge. You're right and you're thinking, but take on the charge of what? What's the charge they become if they lose 2 electrons? They lose 2 sources of negativity. What does their overall charge become now? How much positive? Yeah, say it out loud. 2 positive, okay? 2 positive. Okay, then we skipped on over all across the transition metals because those are weird. Okay, you zoom right on over. Okay, and you go over to halogens. What do we know about halogens, Bryce?
They're unique in bonding.
They're unique in bonding. How so? Ava? Just tell me about halogens.
Oh, I said they're the most reactive of nonmetals.
Yeah, that's kind of why. They're the most reactive in nonmetals. That's kind of what makes them unique. What do they really want, Liam? Which means they take on a charge of min?
Take on a charge. Take on a charge 1 negative. 1 negative.
1 negative, 1 minus is another way to put it. All the same. Drea, tell me something else about halogens. In front of it. So fluorine wants to become like neon in front of it. Juan, what's unique about noble gases? Juan, what's unique about noble gases? I'm pretty sure you came in at this point. This is what happens when I'm actually really tired. I get even feistier. Yeah. No, noble gases. That column 18 or 8A, depending on the counting system.
Everyone wants to be like that.
Everyone wants to be like them. So what about them chemically, Diego? What do we know about them chemically, reactive wise? If everyone wants to be like them, what are they reaction wise?
Neutral.
They're neutral, or what's another way of putting it, Roman?
Non-reactive.
Yeah, they're pretty non-reactive because everyone wants to be like them, so they don't have to make any deals with anyone because they're already perfection, right? So, or so they say. So they say. Okay, so that's kind of your overview. Now let's talk about that puzzle piece. You guys did this puzzle where you tried to analogously through cute little colored circles with spokes, okay, organize the periodic table and it revealed trends. So what do you think the color might be analogous to representing in terms of trends across the period and down the column for various elements? What might the color represent? Density, maybe. What else might the color represent? Maybe reactivity. What do you think the size represents? Don't overthink it. The size of the atom. So across a row, you started noticing that atoms are getting smaller and smaller and smaller. But down a column, you started noticing them get bigger. Okay. What about the spokes? What did we say the spokes represent? Aislinn?
Number of extra. No, I don't know. But
It's okay. What's the subparticle? Number of electrons. And then I always said that there's a specific subsect of electrons called valence electrons that they represent. Okay. So that's where we left off. Today, we're going to talk about those trends revealed in that little puzzle. So make sure you have your notes out, please. And before we get super into this, we're going to watch a quick video on patterns. I'm going to play this video. What you're going to do is you're going to write a little standout point. If you write, by the way, the first minute of this video, you write, I've never known what a pattern was. You're lying. Don't write that. I know what students do. They BS a piece of shizness fact, and they're like, I learned something. Don't do that. This is not PE class first test where you do 5 sit-ups when you can do 10, okay? Actually try to pull something out of like, hey, I've never heard it said that way. Or, hey, this is something that I never thought about that maybe isn't even explicitly said in the patterns video, but you're like, oh, I didn't realize that I can find patterns through looking this way. Write something new out of the video that is either prompted by the video in your brain or actually phrased in the video, okay? Please do not write junk. It's no point in that. So here is patterns. This is, remember, a way that we think in chemistry. We think in patterns.
Hi, it's Mr. Anderson, and this is Thinking in Patterns, Level 2, Patterns of
Why is it like
Change.
this? Why is it echoing? How do I make it not echo? Here, maybe I'll just unshare. Oh, how do I do this? Hold on. Stop Zoom casting, and then I will share the video on my computer. Okay, for those of you watching at home, the video is hyperlinked on the digital notes, so you can watch it on your own. I'm going to pause it for right now. How do I pause? All right, so hopefully you watch that video if you're watching this at home. Again, it's a hyperlink right here. Click on this. And we just watched the first like 5 minutes of it. And so patterns are a really big concept in how to think in chemistry, if you haven't already noticed, right? And so what we're going to do is we're going to look at the patterns. We're going to look at 4 patterns in the periodic table that aren't necessarily explicitly written on the periodic table. They're implicitly structured based off of the periodic table. Okay? So the first thing you need to know is that there's a law called Coulomb's law. And Coulomb's law is a law of attraction. Okay, it's the law of attraction between positive and negatively charged particles or things. So for us in chemistry, specifically, it is a law of attraction between your positive protons, okay, and your negative electrons, whose symbol is, what's the symbol for an electron, Matthew? Yes. Perfect. Your positive protons and your negative electrons. There is an equation provided where we say the force of attraction is equal to some constant K. Doesn't really matter what K is. You don't need to work with it. Okay. Times charge of particle 1. This is the particle 1 charge. Charge of particle 2. All over divided by the distance between those two things squared. Now notice something. Distance has an exponentially weakening factor. This is a weakening. It weakens. Weakens. Weaken by distance. Weaken by distance. So chemistry, law of attraction between positive protons and your negative electrons. You got particle 1, particle 2 charge multiplied by each other, but then divided by, weakened by the distance between them squared. Coulomb's law is the first trend that is actually the main trend that explains all the other trends. So this right here, we're going to start and say this is the underlying trend in the periodic table that explains all the rest of the trends. Okay. So now that I've introduced that, concept, we're going to explore how it affects and connects with other trends. So the first trend, which was kind of obvious from your puzzle activity, is the size of the atom. Not all atoms are equally sized. As we know, if we just consider the fact that there are more subparticles in atoms as we progress down the periodic table, you just have more things that take up space. So you need to put them somewhere, right? So atomic radius is, the distance from the nucleus to the outermost electrons in an atom. Another way of putting that is the valence electrons. Your outermost electrons are your valence electrons. So remember the little chip activity, how we could only fit 2 in one ring, 8 in another, 8 in another? The atomic radius for that atom would be from the center nucleus to the electron that's in the farthest ring. That's your radius. It's not the closest ring, because then you still have some of the atom left. You have some left. So you need to account for how much space it takes up totally. Okay. So, for example, if we look at this, here's the nucleus. Here's ring 1. Here's ring 2. The radius would be all the way out. Right? If I have electrons up to the second ring. If I have electrons that fill up to the second row in the periodic table. Okay. So what do we say? The period trend across a row, right? A period is a row. Across a row, we see as we go toward the right of a period, your radius decreases. it actually doesn't get bigger. It gets smaller, which is what you saw in your puzzle, which is contrary to what we might think. You're adding protons, you're adding electrons. Why is it getting smaller across a row? Okay, here's why. Coulombic attraction and force. Coulombic attraction and force. As we go across a row, what we see is that we increase the protons. And if we look at proton count, protons have a positive charge. They are the pull. They are the pull or the muscle behind the force. So what they do is with an increase in protons, we see that our nucleus is better able to pull in the electrons. So even though there's more electrons across a row, you get more protons. So you get more muscle, you get more Coulombic attraction. So you get more Coulombic attraction. So you pull it in tighter. Notice, we haven't changed distance at all. So far, no distance have changed. We haven't jumped to another energy level. We haven't jumped to another ring. We haven't jumped to another row. All we're saying is across a row, elements in the same row, as you go across, get smaller because there isn't any distance change. There's just muscle change. You just packed on the protein, the proton, the protein, the proton. That's my key for you. The protein, the proton. Juan, you should understand this. You're all about the gains. The more protein you have, the more muscle you have, the better you're able to attract and pull in things. Yes. Oh, hi. Yes. Okay, thank you. So it's for you for seminar. So this is the most contradictory thing that I can introduce to you because initially you think, oh, more protons, bigger number on the periodic table, bigger size. Not if you're just sticking in the same row. If you're just sticking in the same row, then it's, hey, more protons, more muscle, better pull. Right? Okay, so what about down a column? Let's do a group or a column trend. What did we notice in the puzzle activity? Well, we saw that as we go down, okay, a column or barrel, we see that the radius increases. Now, why is that? Aren't I getting more protons? Aren't I getting more muscle? Aren't I getting better at attracting? Yes, except for this one problem. According to the Coulombic attraction equation, distance, radius, exponentially weakens attraction. Kind of like long distance relationships, right? So what happens down a group or a column? You do get increase of protons, but the bigger problem is that you get an increase in the energy levels or the rings. If you think back to our initial little bingo chip demo, you get an increase in the energy level or rings. You have to bump down a level. You suddenly now have to fill up the second row. There's no more seats left in the first row for your electrons. So you have to fill in the second row. And that second row isn't where the first row is. It's a set amount of distance behind the first row. So what happens? Your radius has now increased a set amount. And if you increase your radius a set amount, you have just, according to the equation, exponentially weakened your attraction by a set amount squared. Okay, so if you increase your energy level of rings, your nucleus, okay, is not easily able to attract or pull, okay? So your Coulombic attraction decreases. So I know right now the saying, at least in 2023, is, hey, can you pull? Okay, I know that's a saying. You can kind of think about it from the nucleus perspective. The nucleus is trying to pull in electrons. Okay, more muscle, better pull. But more distance, I don't even care. If you're not eating the same continent, it's not going to happen, right? So same idea with these. Give the particles a little personality, and I promise you they'll register better. All right. Now, what happens when we mess with electrons? We remove or add electrons, right? We take on a charge. Now what you'll see is that for cations like metals are cations, they tend to be. When atoms, okay, lose electrons, what can happen is they might lower energy level or ring. They might go from a 3 radius energy level down to a 2 radius if you remove enough electrons, right? They might lower an energy level or rings. So what then occurs? You have the same number of protons, because we don't mess with proton numbers, but less electrons. So what we see then is that cations, positive charge versions of the same element, are usually smaller because you have the same amount of muscle pulling in less. Okay. On the other hand, an anion, okay, this is an atom that gains electrons. So if you gain enough electrons, you enter a higher energy level or a ring, however you want to think about it. So what does that mean? You have the same number of protons, but more electrons. So what's going to happen to your Coulombic attraction? It's going to decrease. Yes, so anions are negative charged atoms of the same element. Anions are usually larger than the neutral version. So what we're also seeing is that Coulombic attraction has its own trend. We see for atomic radius, it gets smaller across and larger down, but we also see from a Coulombic attraction standpoint, okay, that Coulombic attraction gets stronger across and weaker down. So that's kind of two trends in one little diagram. By the way, this is the type of stuff that you're marking on your periodic table. So you can start to imprint it in your brain. So when I give you a blank periodic table for tests, you can translate that vision onto your blank periodic table without writing on it. You just translate. It's like a little film over your eyes. We're trying to do. We're trying to create a film on your eyes for what to see when you look at the periodic table. Okay, I know you guys probably aren't old enough, but I used to go to a school where we had projectors and you'd put a thin little thing and it would project and we'd lay things over it and layer the info and we'd write with little cute projector markers. Okay, same idea. Okay, so atomic radius is a characteristic of an atom that is totally determined by the Coulombic attraction principle that's displayed in the behavior between positively charged protons, negatively charged electrons. You basically have a principle I just introduced and two trends within that. The principle almost acts like its own trend. Okay, third thing, second official thing, but third thing, ionization energy. This is the energy required to remove an electron from an atom. This, by the way, makes an atom an ion, and an ion is a charged atom. So notice we're not very creative with naming. Ionization energy, the energy it takes to make an atom an ion. The energy it takes to make an atom no longer have equal electron to protons. The energy it takes to make an atom charged. Ionization energy. So what we see is across a period, right, to the right, we see ionization energy increase. And I'm going to abbreviate to IE, increases. Down a column, we see ionization energy decrease. Okay, we see ionization energy decrease. Now let's explain why, according to Coulombic attraction. Okay, with a row across a period, you have, okay, more protons, which means you have more pull, which means you have more Coulombic attraction, which means harder to steal an electron, which means more energy required. Okay, how about down a column? How about down a column? You have, yes, more protons, but the bigger issue is you have more energy levels or rings, right? However you want to think about it. So that means you have less Coulombic attraction, which means it'll be easier to be stolen from, right? If I'm holding on to something and it's right next to me, a thief coming to grab my purse is going to be a little bit harder, right? Put more energy in it. But if my purse is over on the seat next to me and because I don't know, I was saving seats for a friend and I used my purse, a thief could just walk away and I would have to, they'd put way less energy into stealing that from me, right? More energy levels / rings, less Coulombic attraction, easier to steal. So that means less energy required. Okay. All right. Is this making sense? The numbers represent something. Do not just look at the numbers like you're counting like normal. More protons does not necessarily mean bigger. It means better protein, better pull. That's what it means. So it's opposite of how you look at the numbers, because the numbers are actually representing an actual characteristic, not just a counting thing. It's an actual subparticle that it's telling you that has its own behaviors. So next trend, okay? Last trend I'm going to offer you, and then we'll be done for today after doing a little bit of practice, because I know it's a lot of information, is electronegativity. Electronegativity is very similar to ionization energy, but here's the difference. It is the tendency of an atom to attract another atom's electrons to itself when, and here's the key phrase, in a bond. Ionization energy is swipe or no swiping, swoop. Just an atom passing by and be like, psych, mine. Electron negativity has more to do with, hey, we're sharing, but am I sharing well? Like, we're in a bond, we're technically sharing, but like, I just want a little bit more. How good am I at convincing some electrons in a shared unit to kind of shuffle on over to closer to me? Okay. So across a period, we see that electronegativity, symbolized by E/N, electronegativity increases. Down a column, that was definitely supposed to be green. Down a column, we see electronegativity decrease. And here's why. I'm gonna take this, copy and paste. Okay, row, I have more protons, more pull, okay? More Coulombic attraction. I already have everything going for me, easier to attract other electrons. Down a column, I have more energy levels, less Coulombic attraction, harder to attract other electrons. It's like there are some people that have this, like, have you ever met people that are just so charismatic? They seem to just pull in more friends. Like they already have friends and they keep gaining more. It's like, how do you get so many friends? Right? And then there are people that aren't like that. That's what we have here. If I already have a strong Coulombic attraction as an atom, it's not going to be hard for me to attract some other atom and be like, hey, yeah, like come join the party. But if I'm already someone who like can't even hold on to the friends that I have, I can't even hold on as a nucleus, as a proton set to the electrons I have, what is the likelihood other electrons are going to be attracted to that and be like, yeah, I also want to join the hot mess. I also want to join the lack of structure, right? No. So there's a saying, you know, those who have much will get more, and those who have less will get less. It's kind of the principle here. If you're really bad at holding in your own electrons, you ain't going to get more, that's for sure. In fact, you're going to lose out. Someone's going to steal them from you. Okay, so we have a few practice problems. I want you to do all 6 right now. Try it out. Make sure you have an explanation for why for each. And so I want you to shout it out. Okay, A or B, number 1. Number 2. Okay, number 3. Number 4. Number 5. Number 6. Okay, let me tell you why. Which element would take more energy to remove a valence electron? Chlorine or bromine? Chlorine is a higher, or let me put it this way, a lower energy level / ring. So it has more Coulombic attraction, so we'll take more energy. 2, which element would take less energy to remove an electron from? This was, by the way, an electron ionization energy question. This was an ionization energy question. Okay. Which element would take less energy to remove a valence electron from? This was also an goodness gracious, an ionization energy question. And what we see is nitrogen has less protons, so less Coulombic attraction, so less energy required. I'm just writing the whys for the right answer. I'm not explaining the no's for the wrong answer. Okay, this next question, which element is more likely to attract an electron in a bond? This is an electronegativity question. And it would be sulfur, because sulfur is in lower energy level / ring, right? If you're thinking about the model that we did. So higher Coulombic attraction, better ability to attract others. Okay, which element is less likely? Again, this is an electronegativity question. Being able to recognize what type of question you're looking at is going to help you a ton. Okay, fluorine versus oxygen. Well, fluorine has more protons, so better Coulombic attraction, better ability to attract other electrons when already in a bond. Okay, and then which one has a larger atomic radius? This is obviously a radius question. And it would be neutral boron, because neutral boron has more electrons to stay neutral. Okay, radius question, last one. Okay, it would be B, would have the larger because it has more electrons. Okay. Fluorine 1 minus would be larger because it has more electrons. So tomorrow's quiz is going to be on what we reviewed at the beginning of class, what I taught you yesterday, as well as these trends and making predictions. Honors, your 5-minute video or 10-minute video is asking you to consider, what if we're comparing two elements that have both a change in charge and distance? How would we make an argument for which one is probably going to be experiencing higher Coulombic attraction if not only charge is changing, but also distance? So they're diagonal across the periodic table. That's what honors is tasked with, and it's purely argument based. It's, can you identify the correct impact of each change and make a logical argument for which element would have the higher or lower Coulombic attraction? Okay, good job, everyone.